Let's talk about the tiny artificial brain cell that started AI. As we continue with the mathematics of artificial intelligence, we look at the artificial brain cell that started AI, and the learning objectives include the following. By the end of this lesson, of course, you'll be able to explain what a perceptron is. That is already giving the idea away that the tiny artificial brain cell that started AI is what is called the perceptron. So, and then you'll be able to describe how weighted sums are computed. I touched on weighted sums in the introductory video to this playlist. Then interpret the equation y equals sigma of wx plus b, and then explain the rules of weights like w and the bias b. Then understand activation functions, perform manual perceptron calculations, and implement a perceptron in Python. Then explain how perceptrons perform classification. So let's go on and talk about perceptrons, which is the tiny artificial brain the tiny artificial brain that started AI. Now, the perceptron is the simplest artificial neuron and is considered the building block of modern artificial intelligence. So, of course, the idea of neurons come from biology, as you know already. So, it was proposed by Frank Rosenblatt in 1954 as a mathematical model inspired by biological neurons in the human brain. Well, by the way, the word artificial intelligence was first coined in 1954, at Dartmouth College when some mathematicians met, people like not is it James Murray? I'm not sure. There was a James there, and many other researchers. That was the first time the idea of artificial intelligence was coined. So for perceptron to come up in 1958, that was like a progress in the process of coming up with the idea of artificial intelligence. Now, although modern deep learning models contain millions or even billions of neurons, every artificial neuron follows the same fundamental idea introduced by the perceptron. So first of all, they receive several inputs, then they assign importance to each input. They combine the inputs into a single value, decide whether to activate and then they produce an output. So this simple idea eventually evolved into today's deep neural network. So when you talk about deep learning, it's based on the concept of perceptrons. Now, let's talk about the biological inspiration behind perceptron. The perceptron was inspired by biological neurons. A biological neuron performs four basic operations. It receives signals from other neurons through dendrites, then combines all incoming signals, determines whether the signal is strong enough, and sends an electrical impulse through the axon. Artificial neurons mimic exactly this decision-making process using mathematics instead of biology. So in biology, when we talk about dendrites, in artificial perceptron, it is analogous to inputs X. Then in biology, when we talk about synapses, these are weights in artificial perceptron. Then when you talk about cell body in biological neuron, in artificial perceptron, you're talking about weighted sum. When you talk about axon in biological neuron, it is outputs in artificial perceptron. So question now is, what is a perceptron? So a perceptron is the simplest computational model of an artificial neuron. So it is the simplest computational neuron. It is the simplest computational model, rather, of an artificial neuron. So a perceptron is the simplest computational model of an artificial neuron. Suppose there are n input features, x1, x2 up to xn, and each input is assigned a weight w1, w2 up to wn. The perceptron, of course, computes a weighted sum of the inputs and then applies an activation function to produce an output. So now you see you have weights and then you have weighted sums, and then the weighted sum is actually passed through an activation function and then you get an output. So its mathematical model is y equals sigma of wx plus b. Of course, you are used to seeing wx plus b as weighted sum, right? And so when sigma of this now, it means that the perceptron is a function of the weighted sum. So here X is the input vector, W is the weight vector or the matrix or the weight matrix if you like, B is the bias, and sigma is the activation function, while Y is the output. Now let's talk about the parts one after the other. So first, let's talk about inputs. A perceptron receives numerical values called features. For example, suppose we want to classify whether a fruit is an apple. So possible features are things like weight in grams, redness, that's the color, and diameter in centimeters. So if the input vector is now x is 160, 0.97, that means a particular apple weighs 160 grams and the redness is 0.9 and the diameter is 7 centimeters. Every machine learning model converts real-world objects like this into numerical features before processing them. So then we go on to weights. Each input does not contribute equally to the prediction. All right. So a weight measures the importance of a feature. So depending on in this Apple case now, it may mean that the weight is more important than the redness, and the redness is more important than diameter, or in any particular order for that matter. So each input does not contribute equally to the prediction. So a weight measures the importance of a feature. So suppose the weight is 0.01, that is 0.01 is attached to the weight of the apple. Then 3 is the weight attached to the redness, and 0.5 is the weight attached to the diameter. So it means that the redness is more important than weight and diameter. So this means weight contributes very little, redness contributes the most, and diameter has moderate importance. So larger absolute weights indicate greater influence on the final decision. So positive weights increase the weighted sum while negative weights decrease it. So whether it's positive or negative, the bigger it is, the more impact it has. But if it is negative, it reduces you know, positive weights increase the weighted sum while negative weights decrease the weighted sum. Now let's go ahead and talk about the weighted sum now. So you have the input X, then you have the weight WX, and then the weighted sum itself is the WX multiplied by, okay, the weight are the values assigned, right? And then the weighted sum is when you combine everything together in a linearly. So the perceptron first computes a weighted sum of all inputs. Mathematically, Z then is WX plus B. So for individual features now, Z is now W1 X1 plus W2 X2 plus Wn Xn up to plus B. So it means that in this case here, of weight, redness, and diameter. So the weighted sum will be 0.01 plus 1 times 160 plus 3 times 0.9 plus 0.5 times 7 plus any bias that may be in the system, which is this B here. So the value is also called the linear combination of the inputs. So in example 1, for instance, imagine that you have the input vector 2, 4, and the weights are 3, 5. That means that the second input weighs higher than the first input because the weight is 5 and the weight of the first input is 3. So to compute, and if the bias is 1, to compute the weighted sum, you then have 3 times 2 plus 5 times 4. That's 3 times 2, 6, 5 times 4, 20. In step 2 now, you add them together. You have 6 plus 20. That is 26. If you add the bias now, you have 26 plus 1, which is 27. Therefore, the weighted sum, Z, is actually 27 based on the parameters given, based on the values given. Then we go for the bias now. The bias is an additional parameter added after computing the weighted sum. So the complete equation then is Z equals WX plus B. So the bias allows the neuron to shift its decision boundary. Without a bias, Z is WX. So the decision boundary would always pass through the origin, right? So the bias makes the decision boundary not pass through the origin. So adding a bias makes the perceptron much more flexible because it can move the decision boundary to better fit the data. So it doesn't always have to pass through the origin 0, 0. Suppose WX is 15, for instance, that's the weighted sum. Well, not that's just the weighted sum without bias for sure. So if B is 5, that's the bias, then it means that Z is 20. So if instead B is -8, then Z will be 7. So notice that changing only the bias changes the neuron's decision without changing the inputs. So without changing the input, the bias can actually it can sway the decision in some type of way, depending on whatever the bias may look like. Then we go on to talk about the activation function. So after computing Z equals WX plus B, the perceptron applies an activation function. So the complete model becomes Y equals sigma of Z. You know, the other time we saw Z to be WX plus B. So that's sigma of Z or sigma of WX plus B. The activation function converts the weighted sum into the final prediction. Without an activation function, a neural network would simply perform repeated additions and multiplication and will be unable to model complex relationships. So this activation function determines the final result. Now, we have different types of activation functions now. We'll talk about step activation function to start with. The original perceptron used the step activation function, sigma of Z. The sigma of Z is 1 when Z is greater than or equal to 0, and sigma of Z is 0 when Z is less than 0. So when you have Z greater than or equal to 0, you have sigma of Z to be 1. When it is less than 0, you have 0 there. So that means that Okay, yeah, that's what we have there for step four. So the interpretation is that the output one means the neuron fires, and output zero means the neuron does not fire. That's a kind of absence presence kind of situation, a binary situation, where either the neuron fires or it doesn't. So when it fires, we have one. When it doesn't fire, that's zero. This makes the perceptron a binary classifier. So let's have an example of that now. Suppose Z, that is the weighted sum plus the bias. The weighted sum is 6, right? Since 6 is greater than or equal to 0, then the output will simply be Y equals 1. Now, suppose the bias is Z is minus 2 rather. Since minus 2 is less than 0, then the output simply becomes Y equals 0. So for anything less than 0, the neuron doesn't fire, but anything greater than 0, the neuron does fire. Okay, then we go on to talk about the sigmoid activation function. So modern neural networks often replace the step function with the sigmoid function. So instead of having that step function, of course, the sigmoid function is also takes values from 0 to 1, but unlike the step function, which is a kind of switch thing, so it's either an on and off situation, so it's either 0 or 1. But the sigmoid activation function takes values all the way from 0 to 1. So it can take any value from 0 to 1. So modern neural networks often replace the step function with the sigmoid function. Sigma of z equals 1 over 1 plus e raised per minus z. Unlike the step function, sigmoid produces values between 0 and 1. So this allows the output to be interpreted as a probability. So sigmoid functions can actually work as a probability. For instance, if you have sigma of 2, that is 1 all over 1 plus e raised per minus 2, and that is 1 all over 1 plus 1 over 2. That's 1 over 1 plus 0.5. That's 1 over 1.5, and you get something like 0.881. So whatever you put as the value of z, you always get a value from 0 to 1. So sigma of minus 2 is 1 over e raised per 1. Oh, so this will be e raised power minus 2, right? That's 1 over e raised power 2. But here it will be 1 over 1 plus e raised power 2 when when z is minus 2. And that's approximately 0.119, like that. So the values are always from 0 to 1 for sigmoid activation function, which makes it way better than an on and off situation that we have with the step function, which is either 1 or 0. So we then have the complete perceptron equation here. The entire computation performed by a perceptron is this, that y is equal to sigma of wx plus b. Sigma is the activation function. So whether it is a step function or a sigmoid function or some other types of functions we're going to come across along the line in this playlist, rather on this playlist. So the computation follows 5 steps. First of all, you receive inputs. You get the input w. I mean, the input x, which is usually a vector. Then you multiply each input by its weight. So you get your weight matrix or weight vector. And then you then add the weighted values, then add the bias. The next thing, you pass whatever you get as the weighted sum. You apply the activation function to that to obtain the final output y. That's the complete perceptron equation. Y equals sigma of wx plus b, if you like. Y equals sigma of z. So, for example, you have x, the input vector to be 4, 3, and the weights are 0.5, 0.8, meaning that the second input weighs higher than the first input, and you have a bias of minus 2. So if you compute the weighted sum, you have 0.5 times 4 plus 0.8 times 3, then add the bias, that's minus 2. So this is 2, 0.5 times 4 is 2, 0.8 times 3 is 2.4. So that's 4.4 minus 2, which gives 2.4 at the end of the day. So that is just the weighted sum, Z. So you now have to pass it through an activation function. And there are different activation functions. We are going to see them later. Of course, in the opening video, we talked about the ReLU activation function, which takes the maximum of 0 and z. So anyone that is higher between 0 and z will be the value in the case of ReLU. But in the case of sigmoid function, you have to you put it into the sigmoid function. So you have y equals 1 all over 1 plus e raised power minus 2.4. And that in that case, y comes out as approximately 0.917, right? Of course, you have to compute that, right? Let's do that in Desmos and see what it looks like. Desmos. Then we come here, we got z to be 2.4. So here you have 1 divided by 1 plus e raised to power minus 2.4. And that's what we get there, 0.9168. 0.9168, 0.917 to 3 decimal places. So that means that the perceptron predicts the positive class with approximately 91.7% confidence. That is what we get when we pass it through the sigmoid function. Now let's talk about classification now. One of the primary applications of the perceptron is classification. So classification is the task of assigning an input to one of several predefined categories. Examples include spam or not spam. So you want to detect if a particular email is spam or not spam, or whether a particular transaction is fraud or legitimate, or whether a situation you observe is a disease or, I mean, maybe you observe a cell and you want to determine whether it's a diseased cell or a healthy cell, or a particular image you see is that of a cat or a dog, or a student passes or fails an exam. So a single perceptron performs binary classification, meaning it distinguishes between exactly two classes. Typically, output 1 represents the positive class, while output 0 represents the negative class. And that is true for the step function we saw earlier. But of course, for the sigmoid function, so values between 0 and 1, 0 means that's the positive result is obtained with a confidence level of 0, while 1 means the positive result is obtained with a confidence level of 100%. But just like we've got here, 91.7% confidence of getting the positive class of whatever classification we are doing. So let's go on to talk about student pass prediction, for instance. Suppose a school wants to predict whether a student would pass an examination. So, and the features to consider are things like hours of study and attendance percentage. So, of course, whether a student attends class a lot, that's good, but it is not as important as the student studying a lot. So that's why in assigning the weights now, the weight attached to hours of study is 0.8, and the weight attached to attendance percentage is 0.05. So, and the bias here is -8. And then imagine a student has the following information. For the student's information is this, that the hours of study is 8 and the attendance is 90%. So the input vector then is so you have x is 8 and 90 is a percentage. So z is 0.8 times 8 plus 0.05 times 90 minus the bias, which is 8 that we have here. So that means we have 6.4 plus 4.5 minus 8. So if you apply the sigmoid function, so that's sigma of 2.9. If you come back here, instead of having minus 2.4, you have minus 2.9. And that changes that to, so that's 94.8%. So that's 0.948. So since the probability is close to 1, the model predicts that the student will pass. So 0 is fail and 1 is pass, like that. So let's go ahead and talk about a decision boundary. So the perceptron separates two classes into using a decision boundary. This boundary is defined by wx plus b equals 0. So the boundary is wx plus b equals 0. So that is where the weighted sum is equal to 0. So for two input features, this boundary is a straight line. For three input features, it becomes a plane. For higher dimensional data, like 4 inputs upwards, it becomes a hyperplane. So every point on one side of the boundary belongs to one class, while point on the other side belongs to the other class. That's the decision boundary. The decision boundary occurs at the point where the weighted sum is equal to 0. And then we talk about the advantages of the perceptron. The perceptron has several advantages. So it is easy to understand. It is computationally efficient. It is fast to train, suitable for linearly separable data, and forms the foundation of modern neural networks. And by the way, it's good to remember that the perceptron is the simplest computational model of an artificial neuron, like that. So, having understood that whole idea of what a perceptron is like, let's talk about the limitations now. Despite its historical importance, a single perceptron has significant limitations. For instance, it can only solve linearly separable problems. Then it cannot learn nonlinear relationships. It cannot solve the XOR problem, which you're going to see later. It has limited representational power. And these limitations motivated the development of multi-layer perceptrons and deep neural networks. So a single layer has many limitations. So we then have multi-layer. And that talks about the idea of quantum everything. So you have computing, which is good, right? But then you now have quantum computing, which is like layers and layers of computing. Now, in summary, we see that the perceptron is the simplest artificial neuron and the foundation of modern neural networks. its computation is summarized by y equals sigma of wx plus b, where x is the input vector, y contains the length weights. The length weights, I mean, just like the case of the student passing the exam the other time, we discover that we understand, of course, and it's easy, right, to understand that hours of studies are more important than class attendance. So, in as much as class attendance is good, but hours of study weighs higher. Then weight W contains the length weight, and B is the bias. Wx plus B is the weighted sum, and sigma is the activation function, and then Y is the prediction. So although a single perceptron can only solve linearly separable classification problems, connecting many perceptrons together creates multi-layer neural networks capable of solving complex tasks such as image recognition, speech recognition, natural language processing, and autonomous driving. So we have our practice problems, having come to the end of all of that. And as usual, I get to solve two of these problems. So let's see the problems we have here. So I'll be solving problems 10 and 15 for sure. So here you can see the first four problems. So you can see the first four here. Explain why the perceptron is considered the fundamental building block of modern neural network and all that. That's 1 to 4 there. Then we have 5 to, here you can see 5 to 9. You can see 5 to 9 here. Then now you can see 10. I'll be taking care of 10. A perceptron has x equals 475. W is 1 minus 2, 0.5, and bias is 3. Compute the weighted sum. That's pretty easy. So we're going to do that. Then so you can see 15 here also. Explain why a perceptron cannot correctly classify the XOR logical problem. So I'll be talking about the XOR logical problem pretty soon. So you can see the other problems also. Then now you have the rest problems showing on your screen. So let's go ahead and deal with these two problems I have selected. Now let's start with problem 10. Problem 10. So a perceptron has input x, which is 475. The weights 1 minus 2, 0.5, and bias is equal to 3. Compute the weighted sum. Compute the weighted sum. So we go green with that. So solution. Of course, we know that the weighted sum equation is z equals wx plus b. So in that case now, it means we have z, which is w. W is 1 minus 2, 0.5. X is 475. This tells us that the most important weight here is carried by 7, this 7, but it is the impact is negative though, followed by 1, which is the first input here, and the least weighted one is 0.5. So, and then we add the bias, which is 3. Bias is 3. So it means that z is equal to, so here now it's just 1 to 1 like that. So you have 4. Okay, if you like, can just say you have 475 multiplied by 1 minus 2, 0.5. Whatever we have here plus 3. So that means we have z equals 4 times 1 plus 7 times minus 2 plus 5 times 0.5 plus 3, like that. So z is equal to 4 minus 14 plus 2.5 plus 3. So all of that will be 4 minus 14, that is minus 10, minus 10 plus 2.5, that is minus 7.5. Minus 7.5 plus 3, that's minus 4.5. So that's the weighted sum right there. And that's what we are required to compute. So if we're to apply this to the to the sigmoid function, for instance, I mean, if we are to apply this to a step function, it means that the y would be 0 because minus 4.5 is less than 0. If we are to apply it to the sigmoid function, which is not required by the way, so we just come here and change this power to 4.5. So we have minus 4.5 like that. And that is 98.9 like that. Okay. So we are done with problem 10. Let's move on to problem 20. Or rather problem 15. Problem 15. That's more like a story kind of thing. So let's see this. Explain why a perceptron, explain why a perceptron cannot correctly classify cannot correctly classify the XOR logical problem. Okay, so let's talk about that. The solution now, the XOR, that is the exclusive or logical operation. So the XOR, which is the exclusive OR logical operation, produces the following outputs. Imagine that you have input 1, input 2, and then you have the XOR outputs. So when input 1 is 0 and input 2 is 0, the XOR output is also 0. So input 1 0, input 2 0, XOR is also 0. Then when input 1 is 0 and input 2 is 1, XOR input is 1. Like that. Then we have this that when input 1 is 1 and input 2, oh, what did I do here? Input, right? Input 2. So input 1 is 1, input 2 is 0, you get 1 here. Then lastly, if you have 1 on both sides, this is 1, this is 1, the output is 0. So it tells us that the exclusive OR problem is that once there's a difference, once the inputs are the same, you get a 0. Once the inputs are different, you get a 1, right? So they have to be the same. So 0 or 1 is 1. 1 or 0 is 1. 0 or 0 is 0. 1 or 1 is 0. So that's why it's called the exclusive OR. So the inputs have to be totally different for you to get a 1. So with that in place now, since we know what the XOR output looks like, then we can say that a single perceptron separates classes using a linear decision boundary. Which is given by Wx plus B equals 0. Like that. So in two dimensions, this decision boundary is a straight line. So then if we plot the XOR data points, the two classes are arranged diagonally. So you have class 0, which is 0, 0, and 1, 1. Once they are the same, this class is 0. Then class 1 is for 0, 1, and 1, 0, like that. So we see that no single straight line, separate, no single straight line can separate these two classes without making at least one classification error. Therefore, the XOR problem is not linearly separable. It's not linearly separable because a single perceptron can only learn linear decision boundaries it cannot correctly classify XOR regardless of how its weights and bias are chosen. So, to solve XOR problem, we must use a multi-layer perceptron, MLP, with at least one hidden layer. The hidden layer combines multiple perceptrons to create nonlinear decision boundaries, allowing the network to correctly classify all four XOR input combinations. So in summary, right? In summary, a single perceptron cannot solve the XOR problem because XOR is not linearly separable. It's not linearly separable. Since a perceptron can only learn a single linear decision, a single linear decision boundary, it cannot correctly separate the XOR classes. And so a multi-layer perceptron or MLP. Did I write that initially? Multi-layer perceptron. Oh yeah, MLP or MLP. A multi-layer perceptron neural network is required to solve this problem. And on that note, we come to the end of this particular video, talking about the tiny artificial brain cell that powers the tiny artificial brain cell that started AI. So again, look at the practice problems. So here you see everything problems 1 to 4. Then you have, okay, again, problems 1 to 4. Problems 5 to 9. Yeah, 5 to 9. Then problem 10, the one I solved, up to problem 15, which I also did. And then the rest. Let me know how helpful this is for you. If there's something that you let me try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed to this channel, this is a good time to do that. Just go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having known that, you can also become a member of this channel by clicking on join. That gives you some special privileges that you'll find out when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Watch out for the next video under the mathematics of artificial intelligence playlist. Bye.